So welcome everyone. We're gonna have the last session from Paulo Rufino for the course of stochastical calculus. So I'll give you the floor.
Right, thank you, Beatriz. Right, welcome, good morning. Let's start our last lecture or last talk. And I'm going to talk on stochastic differential equation and aspects related to that. And we finish this mini course. I in the last half an hour, I'm going to mention many related results or without proof, just some comments on, especially on geometry. Put stochastic differential equation into a geometric context. But let's start with continuing what we have been doing yesterday. Let's talk on classic stochastic differential equations. So we have sets of semi-martingales and of vector fields. So I am going to assume that we have a sequence X n vector fields, which here I am going to assume that is globally Lipschitz. And RG. And we have the following equation: gxt equals x0. So I am assuming autonomous system, since we can easily convert a non-autonomous into autonomous system, or rather consider it separately if you wish. Xt. This is called the drift part of the stochastic differential equation, plus the diffusion part, which is given by a sum xi at xt integrated with respect to, so it can be with respect to any semi-martingale in principle, but I'm taking our favorite, which is Brownian motion, which is most of equation, or many situations, many martingales can be written as a functional of a Brownian motion. So, and this is in the sense of Ito, which means this integration is performed in the Ito sense, with an initial condition x0 given by a certain point, x0 in Rg, and by a solution of this equation, solution means the integral version of this equation. Means that we are looking for a process, a stochastic process xt, which equals x0 plus integration from 0 to t, x0, xs ds, plus Ito integration of x summation I1 GBS, such that we have n distinct noise being introduced in the equation. It is mind that the way we are introducing if we have an interpretation of a perturbation of a deterministic system, the way we are introducing the noise is we are permanently introducing a Gaussian noise. any interval of time, it's permanently being perturbed by Gaussians, by the increments of this process. Right. So a rough idea of what is going on is that we have a starting point x0. So the solution process is going up or down or going in all possible directions in RG, such that these vector fields xi, they are giving the directions where this noise is going to be applied. So we have a direction x1, a direction x2, direction x3. So in some sense, we can have this intuition that they are pointing where the noise is spreading. It's more than that, but for first glance, it is like that. Lie bracket of this vector field is also directions which we can move into that direction, to that dimension, right? But as a first approximation, think like that we are spreading in directions of this vector field. So as in a control function, as in a control equation, okay? There are many aspects to be explored here. I mentioned some of them. So some of them, existence and uniqueness of solution is one of them. Existence of flow. Of a stochastic flow. Further properties. Further dynamical properties. Which is tens of different areas of research, which we can mention stability. So those trajectories will contract to a certain point, would not local behavior. Local behavior in the neighborhood of hyperbolic points, for instance, like a Hartmann-Grauman theorem. So more or less, many dynamical systems problem, we can now ask for stochastic systems in this context. Linearization, well, in stability, it includes linearization. We can include some, as I said, some how to put in a geometric context. Geometric context. Well, literally, I have tens of things: rotation, invariant sets, ergodicity, asymptotic behavior, conjugacy, possibility to include jumps. So I'm not going to write it, and I just leave it as etc. It is. So essentially, we will start with this. What I'm going to talk today. I'm give an idea for the existence and uniqueness. Yes, we have a question.
Could I ask a very vague question? So the second point you listed, existence of stochastic flows. Is there some intuition when I should expect an equation to have a stochastic flow?
An equation to have a stochastic solution.
No, to have a stochastic flow. So if I understand correct, the only obstruction to having stochastic flow is that the solution is defined for every initial condition, but there's uncountably many initial conditions, so they may not properly interact. So is there some intuition when I should expect something to have stochastic flow?
Right, some intuition of what it is.
when I should expect there exists one and when. So if I just have an equation and I look at it,
Right.
could I just say, oh, this probably doesn't have stochastic flow, and oh, this surely must have stochastic
Well,
flow?
it's whenever it is here, I am assuming smooth, and globally Lipschitz. So if it satisfies these two solutions, it has a flow for all time t.
Okay, and if the vector fields are very rough, then it could be
If it is very rough, it could not access the flow.
Okay.
Right.
All right. Thanks.
Okay. Thank you. It's more than that. I'm not going to use it in a. This is not used to prove existence and uniqueness of solution, but it's absolutely necessary to prove the existence of flow of diffeomorphisms. Differentiable dependence on initial condition, in other words. Okay. So I give you what I'm doing today is to give an idea of existence and uniqueness of solution for a certain initial condition. Well, I'm not going to prove, but I'm going to show the result and how to use this in some geometric context. And then I finish. I more or less technically I stop the technicalities here, and then from here on is just an invitation to fill the gaps on the proofs, or rather an invitation to get more involved with problems, open problems which are related into topics on stochastic dynamics. Okay, depending on your interest on the right. So the theorem. There exists a unique solution up to indistinguishability in the longest word in English, as I said before, in this, which I know, indistinguishability. Is it right? Well, they can be indistinguishable. Distinguishable, so one more syllable. Indistinguishability. Right. Proof or idea of the proof. Is the following is following the classical argument to construct a contraction and whose fixed point is the solution. So we take the space of candidates of solution, the space of adapted process, continuous adapted process. So say space of candidates E continuous adapted process X xt such that expectation, the composition of the two norms, this is finite. Well, the norm here, the norm into the space, or semi-norm, if you wish, this equals square root of that. Sub t xt square. This is, if you wish, a semi-norm in a Banach space. And Banach here means that the quotient which is necessary to transform it in a Banach space is the quotient, the same quotient we need to transform L2 integrable functions into a Banach space. So up to measure 0, which means up to indistinguishability, right? So this tilde is indistinct, blah blah blah. Oh, yeah, you got it. Okay. Right. And the point here, the calculation which I'm not going to do is to prove that this operator from E to E, so given the process U, L of U at T equals x0 plus integration from 0 to T x0 US dt. How many noise do we have? Any, right? N or G, N. Any noise in directions of noise. US GBS. And the difficult part I don't do. The difficult part is that L to a power N, oh, not the same, N to a power capital N is a contraction in the whole space as far as I remember. So we don't have to concentrate in cylinders as Professor Sebastian did yesterday. Is a contraction in the Banach space. Is a contraction for N sufficiently large. And then we are done. Then there exists U, such U in the state space, which there's in E, such that L of U equals U, which is the solution. Which is the, well, in fact, the unique solution. So I'm sorry not doing the details. It will take well, quite long, and you can check by yourself. But it's a beautiful. I mean, philosophically, is a beautiful result in the sense of application of this fixed point Banach theorem. Yes, Martin.
It sounds like the only thing you need to prove it's a contraction.
That's right.
Is the etoisometry, right?
That's right. And Doob inequalities also is used. Well, honestly, there are some details which I don't remember precisely. Etoisometry is one of them. Doob inequality is another one, right? And mind that smoothness is not really necessary at this point. Okay, but it's going to be crucial for existence of flows. Right. Some remarks. Well, an obvious one. Stochastic differential equations are natural source of semi-martingales. Secondly, we start weaken the weaken hypothesis, and if we have locally Lipschitz, is enough for local solutions. It means that it might have an explosion. So it means exists solution up to a stopping time, say tau. And I give you an example. Quite simple. It's quite tricky, and after I give the example, I show how I manage to find a solution of this example. Xt equals xt squared integrated with respect. This is a one-dimensional stochastic differential equation plus xt cubic dt with initial solution equals 1. And check that xt equals 1 over 1 minus bt is the unique solution up to tau equals the infimum of S such that Bs is greater than 1. So how did I know that the solution is like that? So I stayed the whole night doing calculations, and I end up with this example. No. It's much simpler, which is a good motivation to introduce stochastic differential equation with Stratonovich integration instead of Ito integration. That in fact is a quite simple stochastic differential equation, which is simply changing here to Stratonovich and include the little circle here, and everything holds like that. Everything. And we have a conversion formula between stochastic integration, between the Ito integration and Stratonovich integration. If I'm going to apply this formula and see that this is precisely a quite easy equation, xt squared integrated with respect to bt in the Stratonovich sense. Well, and if it is this simple in rules of Stratonovich equation, it's simple like that. So we already know the solution in the classical calculus, and we know that it should be like that. But if you don't believe, just calculate the first and the second derivative, and it fits very well here in the Ito case as well. Okay. So let's talk on this of this conversion between stochastic, between Ito and Stratonovich equations. It's quite useful. You have here a toy example that if it's difficult to solve in one sense, you try in the other sense and get the solution there and then put it back. Right. So this is remarks 1, 2, 3. Third remark, which is the conversion of Ito stochastic differential equation into Stratonovich stochastic differential equation. And I claim that its solution or solutions, depending on the initial condition, solutions of dxt equals x naught xt dt plus xi xt dbti. How many noise? N noise. Solutions of this Stratonovich, or Stratonovich, as the Russians claim. Stratonovich are solutions and vice versa of gxt equals x0 plus half summation in I. I'm just writing the correction term. The correction term is the quadratic variation between this g-dimensional process and this g-dimensional process, which, by the way, we can interpret here as integration coordinate-wise in each coordinate of Rg, if you prefer. So up to yesterday, we were talking about mainly on one-dimensional, and now the interpretation is doing coordinate-wise, and with many vector fields here. Then here it does appear the derivative of di, which is in the direction of xi. All of this is applied in xt dt, and this is precisely this is the Jacobian, which Martin yesterday pointed me that there was a gradient, but not Jacobian. But this is Jacobian, right? Plus the integration, the Ito integration, xt gbt Ito. So that's, or maybe rather write differently, and vice versa. That's badly written, badly English style, right? Conversion solutions are solutions. Well, okay, it's you understand what I mean, right? Well, is it how to do this? Well, a quick proof. A quick proof. One just have to calculate the correction term is half quadratic variation of xi at xt n bi, or the sum of them in summing in I. The same trick we used yesterday. So whenever we want to calculate a quadratic variation, we apply Ito formula on each term to identify where is the martingale component and where is the bounded variation component. And we put the martingale component here against the martingale component there. And we, in this case, we easily get, well, if we apply Ito formula, that will be xi at x0, which is not relevant, is not a martingale. If there is any martingale, it would be here, integration from 0 to t. The derivative, the first order, xs, integrated with respect to xt, with respect to xt itself. Who is xc? Well, this is xt. Plus, well, if we apply, well, this is the guy plus integration from 0 to t, half of the Hessian, or rather second derivative, or I'm just going to represent like that, second derivative of something which is bounded variation, which is not relevant. So these two parts are not relevant. So even here, if we apply Ito or Stratonovich, is not relevant because the martingale part will be here, depending on xt being or being not a martingale, have or have not a martingale component. And when we compare this is a classical and easy trick. I used it yesterday. I'm using it again, and it's a somehow everyday trick which stochastic analysts use to calculate quadratic variation. Then this guy here, is precisely is xi is maybe I should write it better. Well, maybe not. It's if I put in the place of dxt, I put this part here, I get bounded variation plus Ito integration plus bounded variation. The relevant part is the bounded variation. I mean, let me write it one more step. Relevant part is integration from 0 to t dxi applied in the direction of xi, xs, xs dbi against bit. All the other terms vanish. So I just to emphasize this, I put 0 plus this. Instead of 0, you can write it bounded derivative. Sorry, bounded variation. So bounded variation plus the only term which is relevant, which is this one. And this quadratic variation is precisely what is written there, which is which is the integration of dxi in the direction xi dt or ds. Right? Okay. So it is and to realize into story model, just apply this correction term and we are done. Let me make some comments on existence of flow. Or in which sense it exists. I will emphasize the co-cycle property. So, which is another name for this is differentiable. Dependence on initial condition x naught. Which is existence of flow of diffeomorphisms, which normally is local, not global. It's global if in the global Lipschitz condition, but normally it's local. So given a stochastic differential equation, say smooth vector fields, then there exists the stochastic flow of diffeomorphisms phi, which depends on omega r greater than 0, omega r d going to r g t omega x into phi of t omega x is solution of the stochastic differential equation with initial condition x naught equals x. Omega in a set of full measure, which depends on x naught, and Sebastian, and depends on the initial condition, and depends on omega. Depends on t of full measure, which satisfies the following condition, which satisfies the condition that phi that's a bit too much. I am considering here existence of global solution. This is globally Lipschitz. Otherwise, it doesn't exist for all r. Such that phi t of omega is a diffeomorphism. Normally, it is local, as I said. With the following property, which is the cocycle property. Of full measure. And if not global, for each x naught in Rg, there exists U an open set, and phi t into its image Rg is a diffeomorphism. A diffeomorphism whose regularity follows the regularity of the vector fields. So for smooth vector fields, these are smooth diffeomorphisms. For CK vector fields, we have CK diffeomorphisms. And the main property of the flow is the cocycle property. Which says that phi t plus s of omega x equals phi t theta s of omega composed with phi s of omega x. Again, in a set of full measure. This theta s is the shift. Theta s, which goes in the probability space. So if we identify the probability space with the Wiener space of trajectories, f 0t r continuous starting at 0, other sigma, Greek letters for elements in the Wiener space. We have talked about this space that Brownian motion can be constructed in this probability space with the induced measure from Brownian motion. This is called the Wiener measure. And the shift here is simply take an omega and the new omega at time t corresponds to the function omega t plus s minus omega s. So mind that if we have a look at this as a dynamicist, we are looking at the semi-martingale as a controller of the solution xt. So what we are doing here in this cocycle property is that omega is the controller. So you follow the control. The control is given by the increments of the Brownian motion here. So the control is given by its increments, and it says goes up, goes down, goes forward, goes backwards, and so on. So what the shift says is that ignore the previous instruction up to time s. So if you have an omega like that, it means I have already followed all the instructions up to time s. From now on, ignore what has already been followed, and put this segment here. What happens? Put this curve back in zero. So what is relevant is the increments. Then you are putting it back in the same space, such that it starts at zero again, and you say to the system, carry on after s with the same increments, which would happen after time s. This is a way to see a dynamical way to see cocycles. Yes, please, Vinicius.
Sir? Yeah.
Your name? Sorry.
Oh, Gideon. Gideon is the name.
I'm sorry.
Like,
Vinicius. Sorry, I mixed up the names. So.
I had a question about the third board where you define the stochastic flow. So you're saying the omega should come from a big omega, which depends on the initial condition and the time t?
And the time t.
But so how can it depend on the time t?
Can I leave it open? Dependence on initial condition, I am sure, but dependence on t, I'm not. I think Sebastian can explain better. In fact, there is an excellent reference on this, which is a paper by Michael Schweitzel and Ludwig Arnold, where they fix this problem of dependence. Mind that if we do it a countable number of times, there's absolutely no problem. But if we do an uncountable number of times of applying the cocycle property, the sets of measure zero where they don't work could be a set which is relevant. Do you understand what I mean? So when we add up sets of measure zero an uncountable number of times, which happens here,
yeah,
it could fail. So what they did, they have a work from the 90s, fixing this and constructing what they call the perfect cocycle. Which is exactly somehow an answer to your question, which Sebastian, is it? Is
I thought that the definition of a stochastic flow is such that it assumes that you have a set of full measure that does not depend on time nor on the initial condition where these properties then hold. But of course, a priori, when you use ethos theory, then you cannot guarantee that this set is independent of the initial condition, at least. I think independent of time, this you can easily get, but initial condition, I think, is a problem. And these perfection techniques, they remove this somehow. They give conditions under which you can guarantee that there is a set of full measure that does not depend on the initial condition, time,
or also the time. That's As I said, each point I mentioned here has tens of papers which generalize and generalize with much weaker conditions here, much weaker condition for the Ito formula. There is a paper on annals of probability of Ito formula with a continuous function, and imagine how long is the correction term, and it's non-trivial. So what I said, I am presenting the classical case, and each step here, and this is from the 90s, which is Ludwig Arnold and Michael Schweitzel. Is it right? Schweitzel. Yeah, well, right spelling. Z-O-W. Michael Schweitzel, which is in Technische Universität in Berlin, which has worked with Professor Sebastian. So especially this co-cycle property is also tricky when we think on which set we can count with that. So in which sense we can count with that if we apply it many times, but each time we are applying that different set. Did you understand that I didn't answer our question? and
I mean, yeah, I think my question was sort of answered.
Right. Okay. Thank you.
So I have another question, which is maybe just more a point of detail. But the omega that you define as the space of continuous functions, doesn't it allow to represent just one Brownian motion? Since here you have n Brownian motions, do you have to change this definition to define the shift?
Sorry, say again.
So the shift theta s that you define,
the shift,
the space, the probability space that you consider
right,
is the space of continuous functions. So
we
doesn't
can do
it?
it coordinate-wise.
Okay, so we should do the product of n times the Wiener space?
Right, that's
okay.
right. That's
Okay.
right.
Thank you.
Thank you. Thank you. Yeah, indeed.
Maybe if I could ask another question.
Yeah. Oh, yes.
So we are taking t on non-negative real numbers, and then we can define the shift. But the Wiener space there is defined on the compact interval 0 t. Shouldn't it be open? I don't understand it.
No, it's not for our point here is not relevant. So we can just extend capital T longer as we wish. But it's safer. You mean open going to infinity?
Yes. Yes.
Yeah, it is possible to do that, to take T as big as you wish.
Okay.
Right.
How does the identification with capital W work? I mean, omega is supposed to be an abstract space, so W isn't where your random variable takes place.
Right.
So are you saying we have a measure space, omega, P, F?
Oh, yeah. Yes.
And then you're
Yeah.
saying, well, we can think of the probability measure P as, just we take the measure and we look at W, which is like the
That's
space in the codomain or something.
Absolutely.
Is
right.
that the identification you're talking about, if I'm making any sense?
That's right. That's what I mentioned before as the canonical process. Canonical process is defined on the probability space given by its own trajectories. So in the case of Brownian motion, one-dimensional Brownian motion, the canonical process is defined in the space of its own trajectory with the induced, with the appropriate measure. So this is omega t. This is a Brownian motion. It is called canonical process, not only for Brownian motion. Any stochastic process can be seen as a probability measure in the space of trajectories. Right? Okay. I have some topics to mention to extend some. I would like to talk on some geometry here, on how to put this technique into a more geometrical context, and make few remarks on all these tools, all these stochastic analysis tools. So now, if M is M, now I'm changing completely the notation. It's not a martingale, but a differentiable manifold. Differentiable manifold. And we can easily consider a stochastic differential equation on M. So again, x naught, x1, xn, we take smooth vector fields. On M, and what's the meaning of this stochastic differential equation? Xi and I'm going to put a little circle here as a Stratonovich. And what's the meaning of that when we are in a surface or in a Lie group or a manifold in general with a certain initial condition x0? So a solution of that is interpreted in the following way. The simplest way to interpret is not my favorite, but it's the mathematically the easiest. My favorite is the following. I anticipate. My favorite is the following. You take local cards of M. You take a local card phi and a local card psi into an open set in Euclidean space, and there exists a conjugacy of the stochastic differential equation from the manifold M to the Euclidean space, and we can easily we can go from one coordinate system to the other coordinate system. So we can go from here to there, psi composed with psi to -1. Via this conjugacy. I'm going to show it in the last half an hour, and how things works nicely in this context. But the easiest way to define a solution is that for all smooth function, so xt is a solution. If for all f, a say smooth function or C2 or whatever from M to R, f of xt equals f of x0 plus integration from 0 to t x0f, I mean derivative of f applied to x0 at xs dt plus how many noise? N. 1 to n. Xi f xs Satanovich gbti. And this is it makes sense perfectly thanks to this change of coordinate. Changing of coordinates here means that there exists a conjugacy of the process on M to, as I said, to a process on RG, and it's compatible to any change of variables, to any change of coordinates. Which is essentially the same as this definition, applied coordinate-wise. And this is only possible thanks to the fact that we are, well, the simplicity is only possible thanks to the fact that we are using Satanovich integration. Otherwise, we have to take the second derivative of f if we want to apply if our model or our equation is Ito, we will need here the second derivative of f. It means a derivative of the gradient of f. This is the Hessian, and it does depend on the connection. So here we are taking the derivative of a vector field. Derivative of a function f is okay, but derivative of vector fields is only possible with a connection. So we do need geometry, further geometric structure to carry on with the Ito equations on manifolds. Okay, that's why Satanovich is so simple. We avoid this geometrical problem. So in local coordinates, we have d or phi xt, phi from u, psi and phi, say, to the dimension of the manifold. Two coordinate systems. This is phi of x0 plus derivative of phi at x0. I'm writing, no, it's okay. Integration dt plus summation integration from 0 to t, I equals 1. How many noise? N is derivative of phi, applied at xi at the point, well, the notation is getting, I omit the point. The point here is phi of x small x s. And the same for psi. And both are conjugate conjugate in the sense that solution in M can be obtained taking the inverse image of this diffeomorphism, either from here or from there. But are they different? So if I take the solution here or if I take the solution there, are they different on M? No, of course not. They are all the same. That's what I claim here. That when we make the change of coordinate from 1 to there, we end up with the same equation here. We end up with a conjugacy down here. So we have a triangle conjugacy of conjugacies. Okay? Conjugates, they are both conjugates. They are both conjugate to the original stochastic dynamical system. Let's say like that, stochastic dynamical system on M. Original. As compatibility, or just apply phi to -1, apply to phi. We move from this from here. Sorry, we move from here to there, the other way around. Phi -1 psi. Conjugates 1, 1, and 2. This is 1, and this is 2. By compatibility, I mean this. I mean, it makes sense to talk about stochastic differential equation on M, thanks to the independence of the coordinate system.
Sorry if
Yes,
I missed
Martin.
it, but where is your F, your smooth function?
F is inside each coordinate of phi or psi.
Okay, so you're writing for notation sort of phi tilde is equal to your chart phi composed with F or something like that, or phi -1 composed with F.
No, it's
Because you have a smooth function, right, called F, and you have your chart called phi.
right. So this is the mathematical, which is mathematically is good enough to define what is the solution of a stochastic differential equation. But as I said, I have an alternative way to look at that, which is to justify which is more dynamical system motivated. That is the fact that it's independent on local coordinates of the manifold M, which is much better to see solutions like that. Look at solution down here and then push it back to M. It's better to see that way than to see this way, but they are mathematically equivalent.
And you don't need to put the F in your equation there.
No, there is no F there. M here is an open set in M in the domain of the two coordinate system. Okay, so we have U is here, and the solution here up to a stopping time is the solution down there up to the stopping time with respect to this coordinate system. And if you change the coordinate system, we will have the same solution there, and they coincide when we push it back to M. You see, dynamically easier to understand than this technical analytical definition. But, as I said, obviously they are equivalent. Equivalent when we apply f on each coordinate of this. Okay, so all the.
Thank you. One question. In line number 1, you mean Stratovich integral, right?
So, that's right. Thank you.
Right, thanks.
Thank you. Absolutely, absolutely. Yeah. Otherwise, we will have the second order. We will have the connection. Connection is an instruction how to take derivative of vector fields, and we are avoiding this. This is one approach. In stochastic geometry, many people are really interested in the Ito version exactly because of the nice properties they can get of the geometry, of the connection. So they do. So depends on the approach, depends on what you are interested. My intention here is just to show this dynamical system. Say motivation or approach, and but there are many interesting and good papers on this, on Ito equation on manifolds. So let's just in last 15 minutes say very fast some few remarks or final remarks. Properties. Inherited from Euclidean space is that there exists a unique solution up to indistinguishability and up to a stopping time, up to, as usual, stopping time. Either because you go to infinity, or because you, or if you are interested or if we are fixed in a coordinate system, we are in the border of the coordinate system. So there are many reasons to include a stopping time here. Existence and existence of flow. With all the same probabilistic restrictions we had in our N. And if M is Riemannian, then we do have a connection. The Levi-Civita is not the same Levi. Is a way to take derivative of as I said, of vector fields. And we say that xt in M, a continuous adapted process is a Brownian motion if its infinitesimal generator I define it, infinitesimal generator as a Markov process is half of the Laplacian. So in somehow Brownian motion on Riemannian manifolds, it carries information on the geometry thanks to the existence of the Laplacian there. Infinitesimal generator of a process is infinite is A for A in C2 of M, a manifold or in the Euclidean space is the derivative of time t equals 0 of the expectation of f of xt. Which can be easily calculated either as an exercise or yeah, I'd rather so if we apply Ito formula in F, we separate the initial condition, martingale part, and the bounded variation part. When we do that, expectation of martingale starting at is always 0. Then the derivative turns out to be, the constant part vanishes. The derivative turns out to be mainly on the last part of the bounded variation. So that's why it's so easy, thanks to Ito formula, to calculate this infinitesimal generator applied to F. Infinitesimal generator called A calligraphic A of F at a point X equals this. X here means the X naught, the initial condition. It means the very starting behavior of the solution of the stochastic differential equation. I give you some just a formula that is if for an Ito differential equation, stochastic differential equation, we have that the infinitesimal generator equals x0 plus half the sum of gxi xi. By this, I mean plug an f here, plug an f with a certain point x, and then you take the derivative of this f in the direction x0 and so on. And for well, let's just and for a Stratonovich stochastic differential equation, infinitesimal generator equals x naught is the first order term. Sorry, there is some. I'm missing. I'd rather f. Applied to f x0 f. And this is the Hessian plus half Hessian of f of xi, xi, n to n. And here is a of f at a certain point x equals x naught f plus half this sum from I to n xi square applied to f. Mind that this is a second order operator, but it has inside one first order operator by y square f. I means the derivative of y f. This is derivative of y in direction of y. This is a first order applied to f plus y, which takes the derivative of the result of yf. Plus the Hessian. Y. So this is the second order, and this is the first order operator. So what the difference from here to there is exactly the correction term between Ito and Sotonovich. I am running out of time, but it's check that the Brownian motion BT in Rn has infinitesimal generator given by half the Laplacian. And in fact, it is equivalent. Is any adapted process in Rn, continuous and adapted process in Rn with that infinitesimal generator is a Brownian motion. That's the definition of a Brownian motion in the Riemannian manifold. Is a process such that the infinitesimal generator is half the Laplacian, provided we have a Laplacian, provided we have a metric. Well, so 6 minutes to go. There are many dynamical results coming out of here. I mentioned few of them. One or two. So, final remarks. Is that take f from Rn to R. So f is harmonic. I mean Laplacian of f equals 0. Implies, in fact, it is if and only if I'm not proving the converse. If and only if f of a Brownian motion, Bt, is a martingale. So it's a characterization of harmonic functions in Rg, and in fact, it can be extended to harmonic mappings. Harmonic mappings are mapping from Riemannian manifolds to Riemannian manifolds, such that we minimize the norm of the integration of the norm of the derivative, and we use this characterization of harmonic mappings, and we have a result. Is a result by, well, it's in this context of stochastic geometry. that the product of two harmonic measures are harmonic. So if we have F from a manifold M into a Lie group G, this is a Lie group F and G from another manifold going to the same Lie group, and they are both harmonic. We have a stochastic proof. This is with Catuonio. This Pedro Catuonio is around. Is probably coming quite soon. It's in our group here, Catuonio and myself, which says that F, the product in the product space, given X and Y, then Fx times G of Y is harmonic. Is harmonic map. This is somehow trivial in our end, but not for compact manifolds. Well, this is the sort of problems which appear in stochastic geometry. We have also results on foliations. So second final remarks is just a picture, a description. A foliation is locally a stack of submanifolds of a manifold. And a foliated process is a process such that the trajectory lives in one leaf. So if we start at a certain level, it doesn't go out of this level. It means that the stochastic differential equation which describes the system, all the vector fields are tangent to the leaves, and the Lie brackets of these vector fields are also tangent to the leaves. And there are many interesting results here. This is a stochastic foliated process. And one can ask, is it possible to have one equation such that on each leaf we have a Brownian motion, or Brownian motion with respect to this submanifolds? And the answer is yes. Is also a result which we produced here with Sebastian Ledesma. Sebastian Ledesma is out there. Is a colleague of us with Catuonio and Ledesma. And yes, there exists a stochastic dynamical system such that we have simultaneously Brownian motions in all the leaves of it is in a transaction of American Mathematical Society 5 years ago, 6, I don't remember exactly. Thirdly, and the last, I have been working pretty much on decomposition of flow. So write the flow, write the diffeomorphism as two components, depending on what you are interested. One component, you might be interested in some energy level, and this would be, say one component is moving along energy level, and the other component is strictly orthogonal to that. Or one component is an isometry in a Riemannian manifold, the other component contains all the Lyapunov exponents, contains expansion and contraction. Purely expansion and contraction, this is purely isometries. Lyapunov exponents and rotation numbers would be here. So we split into two components. So there are many, we have been involved on many works related to decomposition of flows. So I stop here, and as I said, in the last half an hour, I just went through results which our group here we have been working with, and if you want to know more about that, you are very welcome to contact us. Okay, and thank you very much for all your attention in these 4 days of mini course. I hope it has been helpful for at least some of you. Thank you.
Is there any final questions or comments? No? Okay.
Well, I will be around, and any question, please feel free to contact me. Thank you.
Quero entender essa história do... Porque não fica muito claro para mim como é que você... A gente ouviu
que le viene pasaporte o identidad. Sí, no se sabe si va a tener control, mas puede ser. Sí, sí, sí.
Und zwei treffen uns hier, es gibt einen Parkplatz zwischen dem Convention Center und dem Studentenrestaurant. Da treffen uns zwei, um dann halt in den Sitz vom Netz zu gehen. Du musst halt irgendwie einen Identifikationsnachweis mitbringen. Reisepass. Ja, ja, das soll ich nochmal wiederholen. Dann können wir anfangen.
Okay. So, hi everybody, welcome back. So before we start with the last lecture, I would like to make a small, quick announcement. Today in the afternoon, all of us, except the students from Campinas, unfortunately, we can go to the light synchrotron labs. Yeah? And so we'll happen is that this lecture goes until 12:30, more or less. 12:40 is lunch. And at 2 o'clock sharp, we meet at the parking space between the convention center and the student restaurant. Yeah? So when you, exit the convention center, you will see some stairs going up. So you go up these stairs and there's the parking space. So 2 o'clock sharp, we meet to go together with bus to the light synchrotron labs. And please bring some identification. So for foreigners, your passport, and for Brazilians, your RG. Yeah? I guess we need the actual passport. I mean, maybe it's not needed, but if it's needed, it would be shitty. Yeah. So yeah, please be sharp. 2 o'clock there, because at 2:30, kind of the official visit starts there. Yeah? I guess it's all, no? Okay. Well, so then it's an honor to announce the last lecture of Sebastian. Please go ahead, Sebastian.
Yeah, thank you, Dirk. Yeah, this will be the last lecture on rough path, and I thank you all for coming here again. So we continue with our topic from last time, and so these are the three parts I'd like to discuss. So controlled path, fields of Banach spaces. We're still working in this on this part. Then we will come to the main, I would say, result of this small course, the existence of solutions to nonlinear rough differential equations. And finally, in the third part, we will apply this main result to stochastics. So we look at rough differential equations that are driven by stochastic rough paths, and we will see how you can solve them, and a bit compare with the Ito solution. So, okay, so these are the topics. Okay, so here I record the definition last time, because I don't think that you worked with that before. I've seen that before. So a continuous field of a Banach space is, so you have a topological space here. So in our applications, this will be the rough path space, which is even a metric space. Yeah. And then on every x, every element here is attached a linear space, Ex, and then you have a certain set, a delta of fractions. Sections. So that means, yeah, there are maps. There are all maps mapping from here to the union of these spaces with the, with the property that X here is mapped to the space EX somewhere. And then there are these two properties that are important. So first, if you fix the G that there is a continuity, this is where the term continuous field of Banach space comes from. There are also other fields, I could say here. And then the second thing is the density. When you fix an X and then you look at the particular space here, and you go through all the G, then you would like to have that all the images here are a dense set in the space. And yeah, and this set should also be countable in this definition. Okay, and then we started to prove this lemma here, which gave you a bit of characterization of the space of controlled path, or almost space of controlled path. Remember here I have a space that has two indices, alpha and beta, and they're defined very similar to these little Hölder spaces. So you take a larger beta, than alpha. So these are the more smooth controlled path. And then you take the closure with respect to, so beta are the more, so you have the beta controlled path here, they are more smooth. And then you take the alpha Hölder metric and the closure of these smooth paths here. Yeah, so there's a technical reason why we need this space here. And yeah, so then we can identify a dense set in the space here, which is built as follows. So here take the Young integral. So we integrate here a smooth path with respect to X, and then add just another smooth path. And yeah, there's also a derivative, which is, it's not so surprising that this is the derivative if you know the rough integral. Yeah, again, exactly. So this is the set, and we want to prove that this is dense in the space of controlled path there with these two indices. So we started this. So let me just walk you through a bit quickly now. So we fixed the partition here that has a certain size. Yeah. A theta. So the theta we want to send to 0 at some point. And then we approximate a given path in the space d beta. The given path was the psi and psi prime. So we first approximate the psi prime here, and the psi prime will be just the linear, so the piecewise linear approximation of the psi. Okay. And then we also have to say what is the psi itself, the psi bar, so the approximation of the psi bar here. And there we need to define still, or we have to define here a psi. Okay. Then, and then you have to prove that, okay, this is really an approximation in the sense that you take the difference between them both here in the alpha Hölder norm, then this goes to 0, provided that the mesh size here gets small. And so this is what we want to do. Yeah, and the crucial part here is to prove that the remainders go to 0 here in the 2 alpha Hölder metric. So this is actually not hard to see. So here, what you just have to prove is that if you have a beta Hölder path and you take the piecewise linear approximation, then when you let the mesh size tend to 0, then this converges in the alpha Hölder metric. So not in the beta, but in the alpha. Okay. So what about the remainders? So we write down the remainder here. Still, psi is not chosen. You make some blah, blah, blah. So we did that all last time. And then at some point, we will define here a candidate for the psi. We call this psi tilde here. And this is also a piecewise linear approximation to something. Somehow, yeah. So it's a piecewise linear function, sorry. It's a piecewise linear function. And so then we calculate, so we do something here, we do some algebra, and then we arrived at the following. So at the difference between these two here. Yeah? So these two remainders. And remember what we wanted to do is we wanted to show that this difference here goes to 0 in the 2 alpha Hölder metric. So this is where we stopped last time, basically. Okay, and so there are now some cancellations going on. And so last time I was a bit puzzled about what are the important cancellations. And the important cancellation here is when you look at the differences is that, okay, this term here, this is the important thing. So this term, when you go through the calculation, okay, you have here the row tilde st, and this includes this term here, row tilde tk plus 1 tj. And these tk plus 1 and tj are far away from each other. Yeah? To estimate this term here would not be good, so we don't like this term here. And fortunately, there's a cancellation such that this term here does not appear anymore. So it appears here, yeah, and it appears here as well. So these are the two terms we don't like, and they cancel. So this is the good thing. Okay. And here, to estimate the 2 alpha Hölder norm of this one now is good. So we can do that because either here we have small intervals that we, so here S tk plus 1 is a small interval. Small means it's smaller than the theta. The theta was the size of 2 consecutive points in your partition. Yeah? We have that one. There's also a small interval, also small, also small. Here you have a large one, and this is why I was puzzled last time. But it doesn't matter because here you have a small one. Also, and here you have a large one. Here you also have a small one. So what you do now is you estimate all the 2 alpha Hölder norms of every term here, and so you have to know something about the regularity of these terms here, of course. And I invite you to check that the regularity of this term here is 2. So it's better, actually better than 2 alpha of the, so the psi tilde here has a regularity better than 2 alpha. This also, this has a regularity a bit better than alpha, and this also. And here, yeah. So in total, you really can then obtain that in 2 alpha here. So the 2 alpha was chosen in such a way. So all these here have a better regularity than 2 alpha. So in total, you can estimate then if the theta here, so you have a bit space, yeah, between these 2 exponents. And so you can use that if you have a small partition that indeed this here goes to 0. Okay, so this was fine. And okay, so what I wrote down here is also not completely correct. So there was somebody in the who told me that in the coffee break. So I should have better written here. So it's not true that you can approximate any continuous function, arbitrary closed smooth function in the Hölder metric, of course, if this function is not Hölder. So you should better write here Hölder continuous function. And also what is important here is that you have a weaker metric here. So the alpha Hölder metric, so here you have alpha Hölder, and here you should write beta Hölder continuous function. Then it's true. Yeah. Okay. So that's it. So we've proved that theorem now. So that lemma. So this was very technical, but this was the core of the proof now to see that indeed these spaces form a separate continuous field of Banach spaces. So how is the proof? So we have these C-infinity spaces here before. So remember, we built this dense set with having these smooth functions. So that's why we have here these C-infinity spaces. And we know that these spaces here are separable, so we can find countable dense subsets in these 2 spaces, and we call them S and S prime. So what is our set delta now? So remember, the set delta consisted of functions mapping from the space X or the space of gamma Hölder path to the union here, and they had to have the property that they actually, when you apply a gamma Hölder path, then you end up here in the space of controlled path controlled exactly by this part here. This one has to have. And this is the definition here. So a typical G looks like that. So you just integrate a function phi here with respect to x plus psi, and here the phi is in the dense set of the C infinity function here, and psi is also in this dense set. And I claim, okay, so first of all, it's clear, I hope, that these spaces are then controlled by x. This is, well, this is because you have here the Young integral, and here is the derivative, and when you subtract that, then you have the Young estimate, and this gives you a better regularity of the remainder, so this is fine. This is fine. So now remember, we had to check two properties for a continuous fields. One was continuity. So one was continuity. So continuity meant that, okay, let's fix a G. In this definition would mean let's fix a phi and a psi, and look at this as a function from x mapping to this term here, and take the norm here in the controlled. So the norm here for controlled rough path. Okay, when I do that, you can use that this integral here is actually continuous in the integrator in x, because it's a Young integral. And this is enough to prove then the continuity in x, yeah, as a function of x. Okay, so this was continuity. The second thing was density. So for density, I do the other way around. I fix the x, and then I let the phi and the psi here vary inside the space of controlled paths. But since we just proved that the C infinity functions, so when I index all these maps here in the set here by the C infinity functions, they are dense. I can also index them by S and S prime that are dense, that are countable and dense here. And so it follows also from the that also this density property holds. Okay. And that's it. Okay. So this proposition tells you that indeed is separable. You have a separable continuous field of Banach spaces, but okay, the thing is here that we have to keep in mind that we have different Herder exponents here. So we have a gamma, which is the regularity of the path that are indexed here, and we have a beta, can be equal to gamma, okay, but it's important that we have an alpha that is below. Yeah? So at the moment, we cannot prove that that this is true also for these spaces of controlled path that are defined before, and that are also defined in the book from Peter and Martin, the Freire book. Yeah? So that's why it's a bit a weaker result. Okay, so I try to motivate a bit looking at this structure last time, because I said, well, sometimes there are some measurability issues you face when you work with these different spaces and that are actually random in some contexts. And I motivated that by saying that, okay, so often you have linear maps mapping from this random space to another space that can also be random. So for example, the integration, the rough integration was exactly that kind of map. Yeah, so you integrated a controlled path, and then what came out was also a controlled path. But yeah, so when you apply this now to a stochastic process, then suddenly all these spaces get random, and also these maps here now are defined on random spaces. And when you want to look at the operator norm, then suddenly you don't know, or maybe it's not so, at least it's not so easy to see why this should be random then. Sorry, measurable. Why this is random, of course. It's a random number. It's not clear why it should be measurable. And now I can formulate a proposition you can use for this to answer this question. So let's look at our continuous field of Banach space. Let's look at our delta and assume that we have exactly a rough, so for every rough path, we have a bounded linear map, mapping from here to some space that can also, so I didn't write it down, that can also depend on X here. But in the operator norm, it's, in the operator norm, it's also important. Okay, let's see. Okay, maybe I have to reformulate that. I can reformulate it more general. So we need to, what we need is that another property, we need that taking an element in G, so in the delta, an element G in the delta, then we can look at this map here. And in this map here, we take as a controlled path G of X. Yeah. And then we take the norm. And we need that this map here is continuous. Actually, I think measurable would be enough, but in the applications, we can prove even continuity. So let me assume continuity here for every G. Let's assume that we have a random rough path, and we need also some measurability, of course. And we need that this lift is measurable. Saying that, so for omega mapped to here, so this is a rough path living in a rough path space, yeah, has a natural topology, so there's also a natural sigma field, and we want to have that this is a measurable map, which is given for all these lifts. Well, you saw two lifts, but this is the Ito and the Stratonovich, and for this is okay. Yeah. Okay, and then I claim that the operator norm here is measurable. So the operator norm is measurable. So, and why is it? Well, here I recall you what is the operator norm, and it's a bit nasty because here you take a supremum over elements in a random space. Yeah. That's why it's a bit nasty, and also here these norms here, they also depend on the omega. Okay. Okay, so how do we prove that? The proof is now surprisingly simple if we have all that. So let's look at the definition. Okay, and now what I use is only continuity here and continuity here. So for fixed, I fixed the omega first. Yeah, omega is fixed, and I assumed that the phi here is a bounded linear map, so also a continuous map, of course. So we have a continuity here and we have a continuity here. Yeah. So, but then in the next step here, and this is the crucial thing, in the next step here, I assumed, well, I can, instead of taking the supremum over these elements in this space here, I can also take the supremum over the G's here because I know the density. Yeah? Because I have the density for fixed G. And this is the crucial point, because now by our assumption, so first of all, by the continuity assumption of the continuous field, I know that here, this term here under the fraction, so as a map from rough path, this would be even continuous, but since I assumed a measurability here, then this is only here, this term here would be a measurable random variable. Yeah? And here from the continuity again, what I had to assume, this also follows that this is measurable. So this is actually a measurable function for every fixed G, so for every fixed G. But since I know that I assumed that the delta here is countable, then I have the supremum over a countable number of random variables. So also the supremum then is measurable. So you see, we used really all these properties. I had to use all these properties. Okay. The only thing what we still have to check, I mean, what we don't know yet, if we want to apply that to rough integration, is to check that this map here is continuous. We don't know that yet. So to apply this proposition to the rough integration map, we will have to prove that as well. So we need some stability of the rough integral, at least for a fixed G. And we will look at exactly this question now, but even more general. So but this property then will follow. Okay. Okay, so let me come back to continuous fields of Banach spaces again. So as I told you, it's a quite old concept, has relevance, I think, in C-star algebra. So don't ask me what it is. I don't know. But it's well studied. Yeah. And it turns out that having a continuous field of Banach spaces yields also a natural topology on the total space. So the total space is the disjoint union of all these Banach spaces. So in our case, it would be the disjoint union of all controlled space of all spaces of controlled paths. And we want to describe it here quickly. I will not use it, but okay, I want to mention it to see. You will see why. So there is a projection map from this total space to X again. So this is, well, it's just the map. If you take any element here in this space, would map to the X here. So I call this map P here. And so now we define an open set in the collection of these spaces. So let me do that now. So, okay, so we fix maybe here we have also Z. So we fix an open set in our topological space. So say that one here. So this is the open set in our topological space. We fix a G and an epsilon. So the G gives us points everywhere here. So with the G map. So this is G of X, G of Y, and G of Z. And now you take a ball in these spaces around this G of X, an epsilon ball. And all elements that are in these balls, you put in this set there. So this is the definition of this set there. And this is called a tube. And I think it makes a bit sense because, and this is really an interval, and we have all these spaces that are very close to each other, that this somehow looks like a tube. Yeah. Okay, and the topology you define now on this, on the E, on the total space, is the one that is generated by these tubes. So these are the basis of the topology. And of course, I hope you see now that you can also construct a countable basis easily if you know that this space here is first countable, has a countable basis. Then you could take the epsilon to be in the rational numbers. And since the delta is countable, you can also construct a countable basis. The good thing is that we do not have to work with rough path. In rough path theory, we do not have to work with this topology only, but one can prove that this tube topology is completely metrizable with an explicit metric. And this metric is actually, was defined before, or almost defined before. And this is the one you find in the book from Peter and Martin. Okay, so let's look at the metric. So we take the disjoint union of all the controlled path. I do something now which is a bit different than before. I index them here by rough path, not only by the Herder path as before. Yeah. So here a rough path and not only Herder path. Here I choose, for simplicity, the gamma equal to the beta. So there are no 3 indices anymore, but only 2. Okay, so I take the total space, and then I define a metric. We call that the flat metric here. So what does it do? You take 2 spaces, two elements in 2 controlled paths here that might live in different spaces. Yeah? And you want to measure their distance. So what you first do is you measure the distance between the corresponding rough paths here. So you project them down to the rough path space. There you have the beta metric. Yeah? And you measure their distance here. And then you take the differences here. The differences here, okay, they live in different spaces, so it looks a bit weird maybe to you, but remember that they were just all defined. So these are all just paths defined on the same space. So you can still take the difference. I think we already did that several times, and measure the difference in the alpha Herder metric. And here as well. And then you have also to take care of the initial conditions, because otherwise this would not be a metric, but only a semi-metric. Okay. So this metric I told you was already known, but the nice thing is that you can prove that this is really the one that generates this topology. Okay. So this was in a recent paper that we did. It's not in the book. Yeah. So I wrote this paper with people who are more in geometry than me, and they said it's a very natural name. Let's take the flat metric. I cannot really tell you at the moment why this is. But I'm pretty sure there was a reason. Okay. Okay. So I will not prove that proposition, but you can ask the natural question, well, what about polish? So as a probabilist, you love to work with Polish spaces. You see quite quickly that it cannot be true if you work with arbitrary rough path spaces here, but when you choose the geometric rough path space, they are Polish also. Then also it turns out that this total space here is a Polish space. Good. Okay. And now we can formulate the stability result for rough integration, which is well known, but we can formulate it now in these metrics here, in this regard. So we want to state the stability result for rough integration. And stability means that we have different rough paths here, x tilde, and we have different controlled paths living in different spaces. And then we look at the corresponding rough integrals that also live now in different spaces. Yeah. But we have this metric here that can measure the distances between the different spaces. So let's do that. Let's look at the difference between these rough integrals here. And it turns out that this map is actually locally Lipschitz. So you can bound that by a constant times the difference between the controlled path here locally. So here I wrote locally, which means that there will be this constant here will depend on a neighborhood of that contains these and this controlled path. So in other words, okay, I told you that already, the map, the rough integration map is a locally Lipschitz continuous function on this metric space. Okay, this we can prove. So the only thing, okay, so remember there were several things in this metric here. It looked a bit complicated, but there were first, so there was the difference between the rough path, for example, but the rough path here and the rough path there is the same. So we don't have to estimate there anything. So we have to estimate the Hölder, the Hölder norm of these. So the difference here in Hölder norm, first of all, but this is no, the difference of the Hölder norm of the derivatives here, but since the derivatives here are just y and y tilde, this is also immediate. So the only thing where we have to take care of is to difference the remainders here, is to estimate the difference of the remainders here in the 2 alpha Hölder norm. Okay, so then to do that, we have to go back to how we constructed the rough integral. Yeah. So we call the following, so what was RZ? This was just the rough integral minus this term here, and we used it with to construct with the Ewing lemma. So the I here, the curly I, or the tilde I here is the map from the Ewing lemma, applied to some 2-parameter function psi here, and this was I recalled you here what it was. Yeah. And I was the integration map. Okay, I already told you that. And there's a similar decomposition for the remainder of that tilde, of course, where you replace everything. So you put tildes there everywhere. Okay, so now we use the linearity of this map I in the Ewing map, in the Ewing lemma, which tells us that if we introduce here the difference psi, then the difference here can be estimated by this difference here plus this one. Now this is just the definition and the linearity. Okay, so the Ewing lemma, so we have to estimate both of these terms. So first, the Ewing lemma gives us this bound here. Yeah, it's for free. So, but still, of course, we have to continue to calculate delta of psi in the 3 alpha norm. So let's do the calculation. So the delta operator is a linear operator. So we just have to look at the difference between delta xi and delta xi tilde. And so you plug that in here. And okay, so now we use the triangle inequality. And so what is, so you look at all these terms here and you do the calculation. Yeah, what you see is that really you can bound that by a number of terms, some of terms that are all included somehow here, and so you get a bound in this flat metric. So this is fine. Yeah, and then you have the second term. So you use then the triangle inequality here, and you see the same basically. You have to be a bit careful here, of course, because the C here will depend on some norms here, and the supremum norm of what appeared here. But this is why it's only a local estimate. Yeah, I told you that it's locally, so the C is allowed to depend here on the norms. And this then concludes the proof. Okay, and now we can come back to the initial question. So we still have to settle the continuity of this map here for a fixed G in our set delta to be able to really conclude that this operator norm is a measurable function. It's a random variable. So why is this continuous? Okay, so we have to look at the difference here, or we can look at the differences here of these two. And then you plug in the definition of all that. When you plug in the definition, it was the derivative, the Gubinelli derivative, then therefore you take the Hölder norm of the Gubinelli derivative, And you take the two Hölder, so two alpha Hölder norm of the remainders. So, but they are Hölder norms. So they are Hölder norms. And so we can use the reverse triangle inequality to, so here you have just the difference of these norms, but you can bound this by the norm of the differences in the second step. And then you end up again with the flat metric. Okay, and now, since we have that, we can use our result on the stability of rough integration that told us, okay, we can just bound this by the difference of gx and gx tilde locally. But locally is enough because we only want to prove the continuity. Okay, so now we have to go back to the definition. What was g of x? Well, g of x had this expression for some functions phi and psi. So therefore, we can use, so when we want to estimate the difference of these in the flat metric, so all you had to do is, you have to estimate differences of the integral here, basically. And there you can use the continuity of the Young integral that tells you that you can bound this by, actually only the beta Hölder norm of the x, but this, of course, you can also bound by the norm in rough path. So, and that's it. So if these then are close, then of course also these two terms here are close. Good. So this was it. So this is what I wanted to tell you about controlled path as field of Banach spaces. And now we continue with a more traditional, so what you also find in the book. So this was a bit new, the first part. So nonlinear rough differential equations. So this is the main, our main topic actually. So the main question, how can we settle that? So we want to solve rough differential equations. 12:30, right? Yeah. Oh, okay. I still have a lot of time. Okay. We want to solve rough differential equations, nonlinear rough differential equations, especially. So we first make a definition. Okay. So what is the definition? Well, we give a meaning. Want to give a meaning to this equation here, and this is now very similar to the Young regime. So we give a meaning to this equation by saying that a solution to this differential equation, we call something a solution if the corresponding integral equation here is satisfied and the integral is understood as a rough integral. Okay. Okay, so let's think a bit about this definition. So for the integral to exist as a controlled, as a rough integral, we need that sigma of y here is controlled by x. Then we can make sure that this integral here exists. So we know that rough integrals are also controlled path. Therefore, the solution y itself, if it exists, will be controlled too. Okay? And the natural candidate for the Gubinelli derivative would be just what we integrate. So the integrand, which in this case would be sigma applied to y. So therefore, we would like to consider the following map. So this would be a map we would want to define. And we want to define this map as a map from the space of controlled path to itself. And then in the proof, we want to show that this map has a fixed point. So we want to prove that this is a contraction, at least on a small time interval. So to properly define this map, we have to define it also on the space of controlled path. And so what we would need is to prove that the composition of sigma with a controlled path is again a controlled path. Then we could reasonably define this map. And so we can assume that the sigma here is sufficiently smooth. And so we need a corresponding result, and the result is now this lemma. So this lemma tells you that given a controlled path here, if you have some function phi here that is sufficiently smooth, and what we need is 2 times continuously differentiable, then the composition here is again controlled by x and with a given Gubinelli derivative. So keep in mind that the Gubinelli derivative doesn't have to be unique, but there is one at least, and this is given by this term here. Moreover, if you already know that the sigma here is bounded with bounded derivatives, then you can also give an estimate here of the composition of this controlled path. So in this controlled path semi-norm, depending here on the alpha Hölder norm of the y, and here's the semi-norm of y and y tilde. And the c here will then, of course, depend on the supremum norm of sigma and its derivative. We had to assume that. I should say here at this point that this lemma here is of course, will be useful for us, but what is not so nice and what often causes problems is the square here. The square here, you in many situations you do not like, because it often makes you the life complicated, because you cannot close, for example, a fixed point argument, because you have suddenly something, a square on the right hand side that you do not want. But yeah, it is as it is, I think. Okay, so let's prove that. And so I will assume that already that sigma is bounded and has bounded derivatives, because if it's not the case, you can use some sort of localization where then without loss of generality, you can assume that, because, yeah, so everything is here deterministic. So your function y and y prime, they are just continuous functions. They have some, they take values in some big ball, yeah. So and then you just define the phi, the psi, to be equal on this large ball, and then yeah, then extend it continuously but bounded outside this ball. So this would be the localization. Okay, so let's start to calculate everything. So first we have to calculate the alpha Hölder norm of this composition. So we did that, I think, also several times. Now it can bound by the supremum norm of the derivative times the Hölder semi-norm of y. And so let's have a look at the alpha Hölder norm of the derivative here. So by definition, this is this, okay? And so these are also, they're quite basic calculations here. So use some sort of triangle inequality. So here you have alpha Hölder, here's the supremum, here alpha Hölder. And so finally, in the last line, okay, yeah, so if I have alpha Hölder here, so I can bound that again. Maybe I forgot a term here, I'm not sure. Maybe I forgot a term, so there should also be y prime, the supremum norm of y prime here. I think I forgot the term, sorry. Should also be there. Okay. So this shows that, oh God. Okay. Okay, so we get the estimate here. And yeah, this already shows that really the composition, so we apply the phi to y and y tilde, these two functions are alpha Hölder. And what remains to prove is that the remainder here is 2 alpha Hölder. And the remainder by definition is that one here. And yeah, so you just plug in the definition. This is 2 alpha Hölder we want to show. And okay, so here again, this is just the definition. No, it's not only the definition, because here you replace the y prime here yeah, by putting a y, delta y here, and the remainder. Yeah? So this term here you can replace by this minus this one. So, but now the good thing is that here you can use Taylor's theorem for these 3 terms here. You can use Taylor's theorem. That's why now the second derivative is also important. The second derivative of the phi is also important. And it comes here. So here's the 1/2. This comes from Taylor's theorem, the supremum norm. And here you obtain the 2 in the exponent. Here you obtain a 2 in the exponent. Okay, this term is not so interesting. You can just bound it by these here. So this shows you that indeed these, this composition here is controlled by X, and it also shows you the desired bound when you put that together. Okay. So now we come to the main theorem about nonlinear rough differential equations. Okay, so let's fix a rough path. And at some point, yesterday I told you I will do everything now in a certain regime. And we are exactly in this regime here. So the alpha here is not allowed to be, we assume here only to be between 1/3 and 1/2. Okay? Good, then we have an initial condition. We have some vector field. And for the vector field, I assume that it's 3 times differentiable, bounded, and has bounded derivatives. This is not an optimal condition, of course. Maybe I will come to that, but let's assume that for the moment. And then the statement is that there is a unique controlled path with the property that the y prime is equal to sigma of y that satisfies this equation here. Okay, before I come to the proof, unique here, so the uniqueness, I should say something unique under all controlled paths that have this form here is important. So under all controlled paths for which the derivative is given by sigma applied to y. It's false if you do not have that, because remember the Gubinelli derivative was not unique. So if you had a smooth path here, you could take actually or you have the smooth path here, you could take actually anything here for derivative. So you would not have uniqueness then in the derivative. So, yeah. Okay. So now the proof is really the same. So the idea is exactly the same as for the Young differential, so the equation where we use the Young integral. And it's also very similar to the proof for establishing a solution to stochastic differential equations. When you attended the course today by Paulo, by Professor Rufino, he also said that you prove the solution by a fixed point argument, but on a different space, of course. He proved the solution on a space of stochastic processes, and we prove that here on a on the space of deterministic paths. So what are our spaces? Well, they are the spaces of controlled paths here, where we want to show that the solution exists. And we introduce some notation. So Z and Z prime will be sigma applied to Y and sigma applied to Y prime, and the Gubinelli derivative, which is exactly that one here. And we also take a smaller time here, t0. And we define this map here. Now, So this map here is indeed defined since we know that the composition of a smooth function with a controlled path is again a controlled path, so we can define this integral. And it's easy to see that a solution is a fixed point, or a fixed point of this map is a solution to the equation. Good. And as for the Young integral, we will restrict now this map on a smaller space. So we will look at a closed unit ball here, BT0, that contains all controlled paths starting at a certain initial condition, namely y here, and it's then the y prime here will start at sigma applied to y, with the property that the semi-norm here is less or equal to 1. So this is in the unit ball. And so we have to prove two things as before. The first one is the invariance of this map here. So M is really a mapping from the unit ball to the unit ball, and not only to the whole space, the large space. So this is, we have to do that, the invariance. And the second thing is, well, then the contraction, which tells you, that will tell you that on this unit ball, there's a fixed point, so also a solution. So let's do the invariance. So first of all, these maps here, what comes out really has the right initial condition. You can easily check. So the harder part is to check that also the semi-norm here. Okay, this is also a typo. I have to apply M, Y, and Y tilde here, of course, like here. Yeah. And for doing that, when you remember, how did we do that for the Young equation? We used the estimate for the Young integral. And this is, now we have to use the corresponding estimate here for the rough integral. So for the rough integral, in Theorem 55, we exactly had this estimate here. And this now we can surely upper bound by this line here, where, because this norm here can be bounded by this norm, of course, we want. And here also, so so here we just make this factor here larger by adding also the norm here and here as well, so we can pull that outside. So, and then you end up here with with this term. Okay, remember what was the Z? The Z was the sigma applied to Y. Okay, so now we estimate the alpha Hölder norm of the Z. This is a constant times alpha Hölder norm of Y. And the alpha Hölder norm of Y, we estimate here. So here we use just the definition. So we use this composition of the Y. So delta YS is given as Y prime of S, Y prime of S applied to X, the increment XST plus the remainder. Yeah, this is what we use here to bound. Okay, so when I have the supremum norm, I can also bound this by just taking here the initial condition, but okay, then I also have the factor, I get a factor X prime of Hölder norm. Yeah. I also have a factor here, the alpha Hölder norm of X prime here, but this can be bounded by 1 because I work in the unit ball. That's why it doesn't appear here anymore. Okay, so here I make also okay. No. It's here. It's here. So it's still here. So it's still here. Okay, but the next step we will see we don't need it. Okay, it's also here. Okay, here now I start putting constants. And yeah, well, okay, I think you can do that yourself. And then at some point here I use that this is bounded by 1. Okay, so what remains here is then a bound depends as you can see here on the T0 and on the Hölder norm of our path X. Okay, we want to make that small. Okay, first. Okay, now what? This is mine. It's a bit counterintuitive. Okay, so this was the bound for Z, for the Hölder norm of Z here. So what still remains to bound is the Hölder semi-norm of the controlled path Z, Z prime, because it appears here and here. No? And there we use our lemma 66, which gives us this estimate here. And so we know that this is bounded by 1. So we have the 1 here. What remains is these two terms here. But the Hölder norm of Y, we estimated already in the last slide. And so we see that to bound this term here, so to make this small, one has to do two things. So T0 has to be small, and the alpha Hölder norm of the rough path has to be small. And to achieve that, exactly as before, we first assume that X is a bit smoother and only being alpha Hölder, so that this norm here on 0 T0 really gets small as T0 goes to 0. So in total, then we can guarantee that M really, so the norm here is smaller than 1. So in other words, this M here leaves the unit ball invariant for sufficiently small T0. Okay, so this was the first point. So we still have to prove that M is a contraction. But okay, so to do that, what one has to do is you have to estimate at some point the difference of two rough integrals. Yeah? In this norm here on controlled, it's on the norm of controlled path. Note here that this is actually a bit easier as before. So here the rough path is fixed. So we do not need this theorem about stability of rough integration. So we do not need the full theorem here, because there was allowed that even the rough paths are different. They are different. So we can actually use the easy estimate for the rough integral. And that's also the reason why we do not have to work with these alpha beta spaces here, but only with it's enough to work with the alpha spaces. So the complete proof of the contraction is a bit long. You've seen that in the Young regime. So I will not really do that here because there are no new ideas that are needed. And if you're interested, you can read that up. Still long and technical, but I think you do not learn so much. So that's why I wanted to stop that and just tell you that, yeah, the rest is really the same. So you now have a fixed point on a small, did I write it? No. You have a fixed point on small time. You can now redo that on the parts of your of 0t on the time interval. Then you glue together the solutions, and a posteriori you can prove that your solution is really in the right space. It's the right regularity. Okay. So now there are two other important results I just want to state. I don't want to prove, but I want to state them because they're important when you work with these things. So there's also a bound for a solution to a rough differential equation. And this is an a priori bound, so you don't need to know already that there is a unique solution. You just assume that if there is any solution, then it has a certain bound. Okay. And but what you need is here that the solution is really in the same sense as before, so that the derivative is given by sigma applied to y. If that is okay, you can bound the alpha Hölder norm of the first component here by the rough path norm, basically. And but here you still what you only need here is C2 now, so not C3 for the contraction. Also for guaranteeing existence and uniqueness, we needed C3. And here's also a term which is often annoying, but you need it. It's not only here linear grow. The norm here does not grow only linearly in the rough path norm here, but superlinearly. It's also not so nice in many cases, so just to warn you, but it's actually necessary. So there are counterexamples telling you that you have to have a term like that. For the proof, well, you use the rough integral here. It's done in this proposition here, but it's not so straightforward, unfortunately, because there, what then suddenly poses or makes your life a bit complicated is this square of the composition with the rough path. Then suddenly you get a square somewhere, and then suddenly you have the norm here, the alpha Hölder norm of y here, and you have it on the right-hand side as well, but with a square. And this is, of course, not good, because you would like to have it, well, if you do not have it with a square, but only linearly, then you can make your constant small, subtract it, have it on the other side, and then it's okay. But since you have a square, you cannot do that, and that's why this proposition is quite long and a bit technical, the proof of this proposition. Nevertheless, it's okay, so you can prove that. And there's also a stability result. And we can formulate that as well with the flat metric here. Here's another version of the flat metric with only one exponent. So there's only an alpha here. So here I take beta equal to alpha. Apart from that, it's exactly the same definition. Yeah, and here I also don't need these alpha beta spaces, so I just take the normal ones here. And this is still, you can prove that it's still a metric on the total space. So it does not have this nice interpretation that it's the one that metrises this, the same topology coming from the tube topology, but it's still a metric, so it's okay. Okay, so then the stability result is as follows. So let's take two rough differential equations driven by two distinct rough paths, x and x tilde, and we can also allow two different initial conditions. You could even allow two different vector fields, sigma and sigma prime. So this is not done in the book I'm using here, but there's another book from Peter Fritz, Nicolas Victoire, an older one, where they do that. And then you can see that also you have a continuity not only in the initial condition in the rough path, but also in the vector field. Just a side remark. Okay, and then, okay, so the statement is here, you can bound the difference here in the flat metric by the difference in the initial condition plus the difference in the rough path. And this is a local bound also. So be careful locally here is really important. Okay. So you have a continuity of the rough integration as well. And so, okay, then let's apply it in the stochastic case. So now we did really a lot of theory, and this was mainly deterministic. So this is actually the idea of rough path different to ether theory. I would say that philosophically, you try to keep out the probability as long as you can, do everything deterministic, and at the very end, you let it come in, and then you apply it. There are certain advantages of this approach, but there are also certain disadvantages. Because, well, I would say one disadvantage, for example, is that probability is not probabilistic aspects are not built in your solution concept. Yeah? So that means, for example, when you solve an Ito, so stochastic differential equation, you immediately get that your solution is a nice stochastic process being, for example, a semi-martingale. It's just built in somehow. When you use the rough path approach, deducing these properties later, when you applied all this heavy machinery, often causes a lot of difficulties. Okay. So first thing I would like to discuss is some sort of consistency, saying that, okay, I have a rough path lift, an Ito lift or a Stratonovich lift. I can now look at the stochastic integral or as a rough integral driven by these processes. Are they the same or not? And fortunately they are. So here's the statement. So let's take a d-dimensional Brownian motion. Let's take these two lifts, either Ito or Stratonovich. So we have to be in the right regime here in the alpha. Then we take, okay, so we have to take now integrands that we can use for both integrals here. Yeah? The first thing is they have to be controlled almost surely, because I need this, of course, to define the integral in rough path sense. And for defining the Ito integral, I need that this process is adapted to its filtration generated by the Brownian motion, or could be more generally adapted to a filtration on which also the Brownian motion is adapted to, which the Brownian motion is a martingale. And then the statement is that these two integrals here actually coincide. So the Ito integral coincides with the rough integral, where I use the Ito lift of the Brownian motion as the driver, and the corresponding result also is true for the Stratonovich integral. Almost surely even. Okay. So I will only prove the Ito case. Maybe you will do the Stratonovich case in the exercise session tomorrow. But if not, you can read that up here in the book. Okay, so what do we need to know about the Ito integral? We need to know that it's actually a limit of Riemann sums. This is true in probability. Now, this is important. The Ito integral is a limit of Riemann sums, but not almost surely, but in probability. Not sure if you did that in stochastic calculus in the course, but this is how you can introduce it if you like, the Ito integral. If not, you have to believe me that this is true. And you can now pass to a subsequence, because if you have a convergence in probability, you know that there is a subsequence that also converges almost surely. Okay, so let's assume that we have this subsequence. And so what is sufficient is to prove that, okay, what are the differences of these two integrals here? So both integrals here you can define as a limit of Riemann sums, but for the rough integral, what you also needed was this compensator. Yeah? So that both limits basically differ only from this compensator. And this is the compensator. Yeah. So we have to prove that this compensator goes to 0 in a probabilistic sense. Yeah. So probability would be enough, but we will prove that for L2 even. Because for L2 many things are easy, because then you have this Ito isometry and all this stuff. Yeah? Good. Okay, so we restrict ourselves to bounded Gubinelli derivatives here. So bounded in omega as well. You can do that. You often do that actually in stochastic analysis. You do that first, and later you do some sort of stopping argument to get rid of this condition. So you can do the same here. So we fix the partition here, and then we look at Sk here, defined like that, S0 is 0, and then we define the increment to be these terms here. And you can prove that this is a discrete martingale. Really, by definition, you just take the conditional expectation. You take the filtration that is generated by the Brownian motion. So here you would condition on ftk. And you can prove that this is then 0. So you need just basic properties of the conditional expectation. But here you really need Ito. For Stratonovich, it would not work here. So for a discrete martingale, you know that the increments are uncorrelated. And this you use in this step here. So we take the L2 norm squared. And since they are uncorrelated, and they are also, the expectation is 0. No, it's a bit, yeah, expectation is also 0 of this martingale here, but it's clear. Okay, anyway. So this cross terms here disappear. So this cross terms here disappear, so you don't need the triangle inequality. So you don't need to consider here also cross terms because they're all 0. In the next step, we use this boundedness of y prime. So what remains here is to consider this sum here, but now you use just the Ito isometry, telling you that this is just v times v minus u squared, even squared. So in particular, this is way more than you need to prove that this is a big O of the size of the partition. So when you then let the partition go to 0, this indeed converges to 0. Okay. So now it follows immediately that for a sigma smooth enough, so to make sense of all these, especially of the rough differential equations, then the solution here coincide. And this is just because the integrals will coincide. Almost surely. Good. And now to illustrate or to give you a nice application of what we did, let us prove an important result in stochastic analysis, at least in a certain regime. That is the Wong-Zakai theorem. Okay, so what the Wong-Zakai theorem is telling you is that a stochastic differential equation can actually be written as the limit of ordinary differential equations when you smooth your noise. Yeah? And when you think about it a bit is, you cannot expect that the limit of a sequence of ordinary differential equations is just the corresponding Ito equation, because the Ito equation does not follow the usual rules of calculus. Yeah? So what you could expect is that the limit, that these ODEs converge to the Stratonovich solution because they follow the same rules of calculus. And this is actually what is really true then. Okay, so it has many formulations. I have to say the Wong-Zakai theorem, much stronger formulations that I do here. So I use a smooth sigma, and I use a particular approximation of the Brownian motion. Namely, I use the dyadic points and the piecewise linear approximation. Yeah? Okay, so these are smooth, or at least piecewise smooth processes. So I can look at the solution of these ODEs, of these ordinary differential equations, if I want. Yeah? So they are random ordinary differential equations. And the statement is that these solutions then converge in a Hölder metric to the solution of the Stratonovich SDE almost surely as n tends to infinity. Okay, so this is the Wong-Zakai theorem. How do we prove it? Well, the first thing is we do not look at the ordinary differential equation only, but we look at the corresponding rough differential equation. So we take our Bn here that was smooth and look at the lift to a rough path, to a Hölder rough path for this Hölder. So what we also include now is the second iterated integral. And then we solve our equation here as a rough differential equation. So we did not really discuss that, but there's a consistency. So if your path was smooth in the beginning, then the solution of a rough differential equation, at least the first level, so a solution of a rough differential equation is also the Gubinelli derivative, but the path coincides then with the solution of your ordinary differential equation. Yeah, otherwise, the theory would be very, very strange. You wouldn't like to use it, of course. Okay, so you can do that. So Yn can also be understood as a solution to the rough differential equation here. And we use now the former corollary, which told us that Y, the solution of the Stratonovich differential equation, coincides, almost surely at least, with the solution to the rough differential equation, where I use the driver, the Stratonovich lift now. Okay, why do I do that? Well, the good thing why I will do that, okay, is that I can compare the distance between these two solutions with rough path. Yeah? And so what do I know? What do I know about Bn here and B Stratonovich? Well, I know, and this we proved in proposition 50, it was in a proof, that the Hölder rough path, in Hölder rough path metric, the Bn converges to B Stratonovich. The proposition 50 was where we proved that the Stratonovich lift of the Brownian motion was actually lived in the space of geometric rough paths. There we proved exactly that. Okay, and yeah, so we use now the stability result for rough differential equations that told us that now estimating the difference here. Was there a question? No. Okay. To difference the solutions here in the flat metric, we can, to prove that this goes to 0, it's sufficient to prove that this goes to 0. Yeah? This was the stability result. So this is true almost surely as n goes to infinity. And in particular, only looking at y and yn here, we, by definition of this metric here, yn goes to y almost surely in the alpha Hölder metric as n goes to infinity. Okay, so this gives you a proof now of the Wong-Zakai theorem. My final remark, I want to discuss the fractional Brownian motion because this is how I started to motivate the course a bit. So what about the fractional Brownian motion? So it turns out that in a certain regime, so if the Hurst parameter is not too small, the condition you have to make is that the h is larger than 1/4. Then you can prove that also the piecewise linear approximation of the fractional Brownian motion here, the natural lift, when I take the natural lift here, converges in the space C alpha, provided I choose the alpha smaller than h. Of course, now the limit, there's, well, okay, maybe there is, but there's not a Stratonovich type of a fractional Brownian motion. But you know, since you know that these spaces here are complete, you know at least that there is a limit. Yeah? So to prove that, it's much more involved than what we did. So there are 2 papers at least deal with or giving a proof here. So in the first paper, they give a proof really exactly for the fractional Brownian motion, and there was another paper where they somehow extended such a result to a whole class of Gaussian processes. Basically the same result. So the limit now, you can give a name, say B bold H, and this you call a natural lift of the fractional Brownian motion. So I told you also at some point that just to give a lift of some rough path to say that there's a lift to some path in RD, there's a kind of theorem tells you that this can always be done. But usually there are infinitely many, but it's not clear what is a natural lift. And So since this here holds, you could call that a natural lift, or say maybe the Stratonowicz lift, if you want, of the fractional Brownian motion. And this result now allows you to study stochastic differential equations driven by fractional Brownian motion by using the rough path theory. Yeah. Okay. And so this question is, of course, very natural. You can ask, what happens if I do not have an H that is larger than 1/4? This really breaks down. Also in this paper here, in the first one here, they prove that for H equal to 1/4, then this seemingly natural lift here diverges really in the space, in the rough path space. So it does not work anymore. And of course, there are many, many papers on this question, or at least a few, trying to give other natural lifts maybe, but it's, I would say, still not really understood if there's somehow a natural lift of a fractional Brownian motion for a small Hurst parameter. Nevertheless, there are also many, many papers now studying this kind of SDEs in this regime, this fractional Brownian motion. So if you listen to Professor Rufino's talk, he gave all these questions you can ask about stochastic differential equations driven by Brownian motion. You can also ask exactly the same questions here for the fractional Brownian motion. Okay, so then I'm done with the lecture. Let me finally give you some references. So this is the book where it is dealt, for example, with the fields of Banach spaces. The proof I gave you here is taken from a PhD thesis from Mazia. And so we wrote a paper where we did that actually for every Hölder regime, so much more general. It's also more technical, so I like this proof here more, and I think it's very easy to present here. And okay, so here's the book by Peter and Martin, which is really nice. So if you really want to learn rough path, I suggest you to start with that book, I think. And finally, these two papers where they deal with the fractional Brownian motion, understood as a rough path, and especially the second one here also starts to prove certain properties of this lift of the fractional Brownian motion, compares it a bit to what is known for the Brownian motion. Okay, so this was all I wanted to say in this course. I'd like to thank you all very much for asking interesting questions, and I hope that you enjoyed the course. Yes, thank you.
No. Are there any questions?
So on the last slide about the fractional Brownian motion, you said that H needs to be strictly greater than 1/4. Is it intuitively, why can I go down to 1/4 instead of 1/3?
I don't know why. Okay, an intuition, I do not have an intuition, but if you look a bit in the literature, this bound 1/4, so literature about fractional Brownian motions often appears. So also in other contexts. For some reason, so there is something that goes wrong, or there's somehow phase transition. I don't know what goes wrong with the 1/4. I would say it has also a lot to do with the regularity of the Cameron-Martin paths. So there, for every Gaussian process, there's also a Cameron-Martin space. And you can describe the regularity of the paths, of the Cameron-Martin path of the fractional Brownian motion as well. And I think somehow one reason is that if you want to make sense of the integrating fractional Brownian motion with the Cameron-Martin path, you can do that. So the Cameron-Martin path is a bit smoother than the fractional Brownian motion, and you can do that exactly in the case when the H is strictly larger than 1/4, then you can use the Young integral. Yeah. So I think this is this is somehow a reason, or at least this is what you often have to do. And this would not work anymore. On the other hand, there are statements like, for example, there's a large deviation principle for stochastic differential equations driven by a fractal Brownian motion. And you can prove that exactly in this regime, h larger than 1/4. But interestingly, exactly the same statement can be formulated for every Hurst parameter. So there, the Hurst parameter doesn't matter. So there you could expect that this may be a, because the thing is that when you take a Cameron-Martin path and you want to drive, so you look at a controlled equation where you use as a control a Cameron-Martin path. Yeah, you can do that actually in every regime, in every h, also in small, so for an h arbitrarily close to 0. And that's why you can formulate this this large deviation principle there as well, because the rate function would involve exactly the solution to this controlled equation. Yeah, so it's a bit, still some things are not so clear to me there also. Yeah.
More questions?
I would like to just ask if we could make a few informal remarks about what parts of the course will be most relevant to next week's course on regularity structures, and maybe in what sense.
So unfortunately, I cannot look in the future. so I don't know what exactly is discussed in the regularity structure course. But I think one concept that is really important in both theories are these controlled paths. So having somehow a rough path, and to the rough path we have a space of paths you can integrate. This concept is also important in regularity structures. So you have a model, and then you have model distributions, and they play the role of these controlled paths. So there are also other similarities. I mean, I'm not so an expert in regularity structures, but what we somehow did here, or at least in the linear case, so we made a formal expansion of the equation. In the linear case, turned out that the expansion only contained the iterated integrals. By the way, if you expand a nonlinear equation, you will have also other terms, not only iterated integrals. But this kind of idea that you expand your equation first to see what you actually need for the solution is also, I would say, a guiding idea in regularity structures. So somehow you expand the equation, and then you see, okay, there are terms I can make sense of and others I can't. And then you build up your solution, assuming that you can make sense of these terms and later try really to make sense of them.
Are there more questions? Okay, so maybe, can I make a quick remark to this question? So maybe one similarity I saw, there was this extension theorem of Lyons, and he essentially said, okay, you only need to have the first n iterated integrals, and then afterwards everything is automatic. You n plus first, n plus second, you get automatically. Maybe that's something also similar in regularity structures, where you have an equation, you do a pk iteration. Actually, you only need to take care of the first few terms in the pk iteration. Once you have them, you can control them, the rest is automatic. So maybe that's the philosophical resemblance. Okay. So, okay.
You said that in the case of the rough solution of considering a stochastic process, it is not immediate to get the probabilistic aspects of the solution, right? But considering the fractional Brownian motion, what can be said about it? Is it?
Yeah, one thing, for example, that was open for a long time is the exact regularity, integrability of the solution. So for example, let me go back to a bound. A bound for a rough differential equation. So here. So in E2 theory, at least, you would expect that the solution has the same, or in many cases, if you have, when you have bounded coefficients in your function, you know that the integrability of the solution of your SDE is the same as the Brownian motion. Yeah, it's the same moments, exponential integrability, like that. When you look at this bound here, so this is a deterministic bound. Of course, you can, on the right-hand side, you have a maximum, but you also have this exponent 1 over alpha. And this exponent 1 over alpha is, of course, something which is larger than 1 in most cases. Yeah. So when you only apply this bound to, if you want to deduce an integrability for the solution to a rough differential equation with this bound, you would get a worse one, because you have this 1 over alpha here. So it must be worse. But it's known in E2 theory, it's known that it's the same. You just use if you use the E2 isometry, you can see it when you have a bounded coefficient. And these kind of things I mean. So you have here a bound that is even optimal. This is optimal. You can find a rough path where you really see that you need this 1 over alpha. But there, of course, rough path is very generous. So rough path can be really, really nasty. And often the stochastic processes does not have these nasty paths. And but rough path is blind somehow, cannot see that. And if you want to deduce that really a solution to rough differential equation is the same regularity, you have to work a lot. So you cannot use that bound here, for example. You have to come up with other ideas. Other things are, so maybe you noticed that I had much stronger regularity assumptions here. In Paulo's last theorem, he assumed Lipschitzness of the coefficients. I had C3, which is much stronger. Yeah, and this also has and the reason is, okay, C3 you can relax these assumptions, but not so much. So 2 plus something will still work. There's a reason behind it, because, for example, you get the flow property here for free. And in Paulo's talk, he didn't have the flow property, and he told you that if you want to have the flow property, you need more regularity, for example. So it's quite reasonable that you have strong assumptions here. But still, I think the reason why you have stronger assumptions is also that this rough path can be so nasty that you have somehow also to deal with very nasty rough path, others than the Brownian trajectory, which in many senses are not so nasty.
Are there more questions? Okay, so then let's thank Sebastian again. And well, so that's it. So just to remind you that at 2 o'clock sharp, we will meet at the parking space between the convention center and the students' restaurant. And bring your passport or some identification. Okay.